This is a lesson on spectroscopy and stars. So light from stars can be analyzed using a spectroscope, and it can tell us a lot about its properties. And what a spectroscope typically involves is passing light from a star, okay, through a telescope and into prism setup with eventually with the light being split into its constituent wavelengths, and that light is then sampled electronically at each particular wavelength that comes out, okay, and it's digitized. This is the modern what's known as the modern spectrograph. Okay, the modern version of a spectroscope. It's called a spectrograph. It takes images of the spectra of light, and it can be stored and retrieved for later use. And now, the wavelength of maximum emission from a hot object like a star is related to the temperature of the star via what's known as Wien's law. Okay, Wien was a German physicist. It's a very simple formula. It's on the HSC formula sheet. Lambda sub max is equal to B over T, where lambda sub max is the wavelength where the emitted light intensity is the greatest. B is just a number. This is known as the Wien's displacement constant, and it's got units. So it's basically 2.898 times 10 to the minus 3 meter Kelvin, not millikelvin, meter Kelvin. I'll tell you why in just a moment. And capital T, this is the absolute. So absolute can be thought of as the actual temperature. Okay, absolute temperature of the object surface, in this case a star, measured in degrees Kelvin. Okay, so the Kelvin is the SI unit for temperature in physics. So what this formula is basically telling you is that a short wavelength of emitted light corresponds to a high temperature, and vice versa. Okay, and it makes sense because light with a short wavelength has more energy. So short lambda equals more energy, and that equals more temperature. Okay, by definition, temperature is a measure of the average kinetic energy of particles in a substance, right? So the more energy, the higher the temperature, and vice versa. Longer the wavelength, long lambda, corresponds to less energy because there's less peaks packed into a specific space. That corresponds to less temperature. Now back to the Wien displacement constant, okay, the number. Why has it got units of meter Kelvin? Because if you rearrange the formula for B, the Wien displacement constant, you'll find that it's just lambda max sub max times T. And lambda sub max has units of meters, the meter. And T, the absolute temperature, is Kelvin, so you get meter Kelvin. Okay, that's where you get the units from. Very simple formula. So using a spectrograph, we can actually measure the peak of the black body radiation curve of the emitted radiation by the star to determine the star's surface temperature. What do I mean by that? Well, if I was to plot wavelength lambda on the x-axis, and suppose I have intensity, okay, I, in arbitrary units for argument's sake, and suppose light's particular wavelength of light is being emitted from a star, and it's got a corresponding peak at some intensity and wavelength. Okay, you can work out the wavelength, okay, using the spectrograph, okay, using the digitized spectrum, I should say. Knowing wavelength, you can then work out the temperature simply using Wien's displacement law, Wien's law. Lambda sub max is equal to B over T. More on black bodies later on, but a black body is basically an object that absorbs all the radiation that falls on it, but reflects none. Okay, so it's a perfect absorber of radiation. And stars, to some degree, are black bodies. Okay. So that's where spectrographs come in useful, okay, for determining things like the temperature of a star. Let's now get into the Doppler effect. So back from Year 11 preliminary physics, from Module 3, waves and thermodynamics, the Doppler effect is basically, so in the context of light, it's basically when the observed frequency of light changes when there's relative motion between a source and an observer. So suppose you have a star in this case, and here's the Earth, an observatory, an astronomer standing there. You can actually use the Doppler effect to determine the motion of a star, whether it's moving towards you or moving away from you. And so just like the Doppler effect in the context of sound, you've got the optical Doppler effect causing light waves to shift to longer frequencies, the red part of the spectrum. So in physics, okay, red corresponds to long wavelength, blue corresponds to short wavelength. This is when an object is moving away from you, in this case a star, the optical Doppler effect tells you that the light waves shift to longer frequencies, okay, to the red part of the spectrum. And vice versa, when the object, the star, is moving towards you, the waves get compressed. Okay, and this is called blue shift. So red shift and blue shift. So let me sketch here. The star is moving towards us. Because it's moving towards us and light is being emitted, the light waves get squashed like this. So the light waves get blue shifted. If it was moving away from us, the light waves stretch out, and this is called redshift. So light rays getting redshifted. And so you can determine the amount a star's light has been redshifted or blue shifted by simply comparing the absorption lines in a star spectrum with the known spectral lines emitted from elements on Earth. Okay, so we can use lab-based measurements of known spectral lines that are emitted from elements, certain elements like sodium, and compare those with the absorption lines in a star's spectrum. Okay, because stars absorb particular wavelengths of light. Okay, their atmospheres absorb particular wavelengths of light. They tend to be cooler than the core of the star. Okay, the core of the star is basically a nuclear reactor. It's a nuclear furnace that emits energy, and that energy makes its way to the outer part of the star, to the atmosphere. So here's the core, surface, and then the atmosphere, and that heats up elements in its atmosphere, and those elements, the atmosphere then absorbs particular wavelengths. So you'll see dark lines across a rainbow background, and that's called an absorption spectrum, if you recall from previous videos. And those missing lines, you can actually work them out back on Earth by looking at colored lines instead. Okay, looking at an emission spectrum. So the emission spectrum, the lines correspond to the missing lines in the absorption spectrum, and that's taken to determine what elements are absorbed by the star. You can also, so that's what's called translational velocity of a star. So we can actually work out the translational velocity of a star simply by looking at its spectra. You can also find the rate of rotation of a star. And here's how. So suppose you have a star that's rotating. One side's moving away, one side's moving towards us. So in other words, one side of the star is receding. Receding means moving away. And the other's moving towards us. And then, so therefore you have the wavelengths of the emitted and absorbed lines broadened by the red and blue shift caused by the rotation. Okay, so the receding part of the star will have its light red shifted, and the part that's moving towards us will have its light blue shifted. And the wavelengths of the emitted and absorbed lines will be broadened, okay? We get a bit fatter, okay, due to the motion of the star, the rotation. You can also work out the density of a star's outer layers. And this will also affect the depth and width of the absorption lines. Now in denser gases, remember denser basically means heavier, the particles are closer together. So dense, particles are much more closely packed. Not so dense, particles are a bit further away. So if the particles are closer together, that means you have a higher rate of collision, particle collision. And you'll therefore get broadened absorption lines in a star. This is known as pressure broadening. Pressure broadening. Okay, pressures, if you recall back from year 11, a measure of how much stuff there is in a particular volume. Okay, the more stuff there is, the more particles, the greater the pressure. Okay, think about the atmosphere. So at sea level, atmosphere is dense relative to the atmosphere, let's say an altitude of 10 kilometers. Okay, there's less oxygen, less gaseous particles up there. And pressure broadening is pretty useful because it can tell us about the density of stars, the density of a star's outer layers. Right, so the spectrum would have broader lines. Okay, and they'll tell us whether or not the star's outer layers are dense or not. So very useful indeed. Use of spectroscopy. You can work out things like density, rate of rotation, translational velocity, and also the temperature of a star.